Okay, I'm going to talk to you about our experience with DES on photometric and astrometric calibration algorithms and what we've learned that might be of interest to the audience today. Okay. So I will talk about astrometry and photometry. First about, the trade-off between just making positing some functional form versus just building a big lookup table from the many, many billions of stellar observations that LSST will have. And I will make a distinction between things that are kind of steady, like instrument distortions, versus stochastic things like the atmosphere. And if there's time at the end here, I'll talk about some sky subtraction and some other aspects of sky noise that we've been looking into lately. There's a lot of DES detrending algorithms that I won't cover. And if anybody's interested in those, they can talk to me or one of the many other people who worked on this with DES. And on this page, I put references to the published papers that basically contain nearly all the information that I'll present today. So you can come back and look at these archive links for more details. All right, so what we're trying to do in astrometry and photometry is essentially find two functions that the photometric one essentially describes a flux 0 point, or the transformation from an ADU on an image into an actual physical flux level, as a function of the pixel coordinates on an exposure, x pix, y pix, and t here means time or exposure number. You can take your pick, okay? And also these functions may need to know something about the SED of the object, which I've abbreviated here as color terms, right? And the astrometric version of this is the same idea, but just with two numbers that you have to get out instead of one, RA and DEC. And in fact, the algorithms that I'll describe for photometry and astrometry, they share a lot of the same code because they're essentially doing the same job. Okay. But there are differences as far as what the atmosphere does and what kind of external references we have. Okay, so we need to make these functions for each exposure across the array. And the first question you might ask, let's talk about astrometry, for example, is why not just take the truth from, say, the Gaia catalog for all the stars and just build a lookup table by comparing the Rubin observations to the Gaia values for a selected set of stars, make some gridded function or something like that, and save yourself the trouble of trying to understand why you ended up with that function. And that would work pretty well if there were enough stars, but basically there are not. So there's about one Gaia star per square arc minute per exposure. And a lot of the functions that we're looking at have structure on scales well below an arc minute. And they also have color dependence, and your measurements of the Gaia stars aren't noiseless. So there's extra dimensions to fill in and some averaging that you would want to do. And so basically this technique might work for things that are tens of arc minutes in scale and are different from each exposure, but they would not work for mapping each exposure independently. So what we're going to do is to try to exploit the fact that some components of this function vary slowly, either over time or over space, that is sky position, and so that we can combine many Gaia stars to gain more data, more observations per degree of freedom of the model. That is, we can gang the Gaia stars together, as well as gang the internal observations, the internal consistency observations, right? Okay, so thinking about what these functions are, we kind of can mentally divide the components of these functions into three categories. There are the static things that we could consider to be basically the same over many weeks or longer of observations, although these static functions might depend on known time-dependent parameters like the air mass of a given exposure. And then there are going to be other variables that do vary from exposure to exposure, but maybe have low order spatial dependence. For instance, the 0 point, the overall 0 point of each exposure can be considered free. And that's what this FGCM, one of the things or a linear slope across each exposure. Astrometrically, we can think of the pointing or rotation angle of each entire exposure as being free parameters that we can fit. So in other words, there's only a handful of these per exposure. And then in the last category, I put things that are stochastic, which do vary from exposure to exposure, but would require many degrees of freedom across the focal plane to describe just for one exposure, right? So we're gonna treat these things a little bit differently in our algorithms. So let's just ignore for a moment those stochastic things, and because they're stochastic, we can, for the moment, just consider them to be an extra source of noise to all of our measurements of individual stars that we will add on top of the true statistical noise from photon statistics. And the techniques that I will describe to you for deriving these fixed components, there's nothing really special algorithmically about this. It's quite straightforward. It's just a chi-squared minimization where we are going to minimize the residuals delta x between some truth value for each star and what a model that we create predicts for them. Okay, so this model is going to be, if you look at the second line here, is going to be a function of, here I'm writing this for astrometry, but you can write parallel equations for photometry, okay, where the x's are magnitudes here instead of positions. But anyway, in this, T is an index over exposures, alpha is an index over stars, or what Rubin people would call objects, right? And C is a color. And then our model might include some parameters that stay the same for all exposures and a few other parameters that might vary from exposure to exposure. So all we're going to do here is a giant parameter minimization using here this covariance between the observables, right, the X and Y position basically on the array of each detection. And we'll do some outlier rejection. You know, we're going to be minimizing this, so we're going to have a quadratic solution to do, which means doing a Cholesky decomposition. And that's going to be the only thing in this algorithm that does not scale linearly with the number of observations that are going into this solution. And I'll just say here in the last line that in the astrometric case, the truth, right, for a given exposure of a given star, if we're doing stars and we're doing observations that are spread by more than a few weeks, we have to not only have a free position for each star, but we're going to need a proper motion and a parallax for that star. Right? So this is what I'll refer to as 5D solutions. And this is one thing that's not in the published papers, but we now do in DES. Now that we have 5 years of data, we have to allow for proper motions and parallax of all of our stars. And that's certainly the case for the Rubin things. But the good news is a byproduct of this is that you get a full proper motion and parallax catalog for your entire survey, right? Which is one of the science products we want to make. Okay, so we just have to minimize this chi-squared. So let's think about the parameter counts. The static functions are things like polynomials across the array for astrometric distortions or scattered light in photometric cases, things like that. And you have things like the positions of each of your or color terms that are specific to each of your CCDs. You have atmospheric chromatic refraction terms to put into astrometry, stuff like that. And we have code that you can build yourself an essentially arbitrary model for the astrometric or photometric function by compounding a series of transformations. And it's all object oriented, so you can create a new function by compounding another set of parameter models if you want. Okay, so what are we going to end up with? Well, the static things that describe the array for each filter where we want to make a solution here, we're going to have a few hundred or maybe 1,000 or so static parameters that describe all the polynomial coefficients and stuff that we need. Then on the exposure terms, we might have something like a constant or say maybe as high as a cubic order polynomial for each of these functions that we're gonna allow for, you know, some things like, well, the weather can actually affect, for instance, the astrometric map. And so that's about 10 or so parameters per exposure. We're going to be dealing with many thousands of exposures, so that gives you tens of thousands of free parameters in this solution. The chi-squared can also include external data like Gaia, so that really does not change the nature of the solution at all. But the last thing they'll say is that in the equations that you saw, there are free parameters for each object, either its intrinsic magnitude or its 5D stellar parameters in the case of astrometry. And the way that we avoid having millions and millions of free parameters in the solution is that we analytically marginalize over that truth on the fly so that it never enters into the solution, because all of those parameters enter into the chi-squared strictly quadratically. Okay, so the algebra of marginalizing is done before you build your covariance matrix. Other computational details, all of these models are coded with derivatives so that you can do a Newton iteration in every time around. We have to do outlier rejection because there are lots of bad star measurements or variable stars or things like that that you're going to throw away. This code that I have is fully parallelized for shared memory. Most of the per star calculations are trivially parallelizable, and we've done that. The only tricky thing is that you're accumulating this gigantic covariance matrix or A matrix in the solution, and you have to be careful about parceling out access to that matrix in a synchronized fashion. So I have a fine-grained lock on that. And there's some numbers here to basically say that when we do this for DES, I can run it on one node of a cluster in a few hours. So we're not anywhere near a situation where this is a computationally limited problem for the whole DES, which is a mere 100,000 exposures compared to what LSST will end up with. Okay. All right, so let me get into just a little bit more of the model details. We have this table here, which is from one of the papers, lists the components of the photometry model. And you can see that there are some things here, tree rings and serial edges. Those are detector effects. And then there's some polynomials to represent the optical CCD and its color terms. We have exposure level things, the 0 point, a color term, and an extinction gradient, atmospheric extinction, that is, across each exposure. And then we have some terms that represent the drift of the response or of the instrument over time. Okay. All right, so just jumping to some results here. These are photometry results. This is what the photometric solution looks like. And so what you see on the top is what we call the star flat. This is what Robert showed yesterday. This is the ratio of the response to true focused stellar light compared to what the dome flat gives you, right? And you can see these donuts, which are basically removing the presence of unfocused scattered light in the dome flat. And then on the right side in Y-band, you can see a strong chip-to-chip pattern, which is because the color of the stars is different from the color of the dome, and the Y is in particular very sensitive to that, right? Second row here shows color terms, and the bottom shows the binned residuals to this model. And you can see it's quite good. The scale is millimags here on the right. And you see there's a little bit of residuals where our functions are not following the donut edges very well in G-band, but that's good enough for us. There's something weird in Y-band. You see a lot of structure there. I'll jump here. This is an average of the Y-band over all the CCDs. Notice the scale on the right goes plus and minus 4 millimags. This is a photograph of the board to which all CCDs are glued, and you can see that the features we see in the Y-band stellar flat are due to reflections off of traces that are, you know, changing something a little bit that the dome flats didn't catch up, right? So the stars, I will point out here, basically are better at telling you the response of the instrument than anything else that you can construct, right? Okay, so just going back up here, I'll also mention this is a map over time with dates across the top row, showing how the response of the whole field of view changes at low orders, and also in the second row, a little bit of CCD to CCD drift over the course of years. And so in Rubin, you'll probably, you know, want to be regenerating these kinds of solutions on a scale of weeks to months. I mean, the nice thing about the telescope is it takes lots and lots of exposures, so you'll have the data to do this. Okay. I think I'll skip. This is just showing you a picture of what tree rings look like in a flat field. And also these are functions here of how the response, the photometric response, changes near the edges of the devices. I believe that the LSS TCAM devices are a bit better than DCAM devices as far as these being less severe. Okay. Last thing I want to mention about photometry is if you take a real close look at your dome flats, you see this, you know, pixel to pixel stuff that does not get smaller as you take more and more exposures. And you can also see that the pattern repeats from band to band, grizY, going from left to right. And so that means this is not noise. This is actual changes in responses to a flat field. But we pretty strongly believe that this is not a QE change. This is just variations in the size of each pixel due to, you know, what I'll call lithography noise in the device. And so this is real, it's here. It's, as you can see, a kind of a fraction of a percent RMS, particularly in the bluer bands where the pixels are shallower. And there's some thought to go into about, you know, it's maybe better not to use dome flats at all. That's the point of discussion, because you're adding this form of noise in to your calibration that wasn't there to start with. Okay, so some results here on the left in the photometry is what is the RMS of repeat measurements of stellar magnitudes above the expected shot noise. And you can see that we reach a floor of about 2 millimags, which then grows as we go to fainter objects. And that growing part to the right, we can pretty clearly assign to shot noise in the photometric sky annulus, right? So those are errors, shot noise from the sky estimate, actually. But the calibration part itself is down to 2 millimags. And if we do a 2-point correlation function, we can see that any kind of photometric error with a correlation length of more than about 10 arc seconds is down also, you know, at about 1 millimag. Notice this is a correlation function, so it's square millimags, right? So essentially what this means is that the calibration, the local calibration of the device is shot noise limited for any star with signal to noise less than 500 in a single visit, which is really quite good. I don't think that we get many stars. I don't know if LSST can measure a star at higher signal to noise than that without being saturated. So in some sense, this calibration is perfect. Okay, so that's what we do with the terms that don't vary very quickly. Then there are terms that are stochastic, and this very complicated plot here is again a time plot where each tick mark down here is an hour, and these are just different epochs along this x-axis separated by the dashed lines. And what I'm showing here in the x's that you can't see is how much the 0 points of the exposures appear to shift from exposure to exposure, and you can see it's 5 to 10 millimags. Now, so what is this, you know, short time scale, 2 minutes apart or a minute apart exposures that change by a few millimags? What's that due to? And I should say these are all clear nights, okay? And what we found is that that fluctuation of the x's correlates very closely with the amount of light that's between 6 and 8 arc seconds, aperture mags. I should mention that all of our calibrations are done with 6 arcsecond apertures. So what we find is that the fluctuations in the x's up here are very highly correlated with the amount of light in the outer annulus here. And what that's telling us is that most of the stochastic errors in the photometry are actually aperture corrections that are changing with time. And so you can regress the x's against these things and basically find that you can measure using this outer annulus, you can recalibrate the aperture corrections on the fly and reduce the exposure to exposure residuals to the solid dots here and get the stochastic part on a clear night down to a couple of millimags RMS. Okay. This is even true for stochastic things that vary across the focal plane within one exposure. And so this is a rogues gallery of 10 exposures of DES that showed significant clear night photometric residual variations across the array, with the color scale showing you the the amount, the area average map of photometric residuals. Each circle here is actually a dot that's filled with the value of this outer annulus measurement. And you can see that spatially, the dots match the map that they're on top of, which tells you that across the array, you can also measure spatial fluctuations and correct for them in the aperture correction. Right? So the atmospheric stochasticity in the photometry is well traced by this aperture magnitude, the outer annulus. Okay. And the last job of the photometric calibration, I won't talk about very much because Eli's going to talk about this, but that's to tie all the exposures together in a uber-cal style thing with another, a larger chi-squared minimization. And I'll let Eli say more about this, but I'll steal my favorite plot from him because I think it's so amazing. This is the large scale difference between DES measured magnitudes of stars and Gaia measured magnitudes of stars. Completely independent measurements. Okay, there's no data or techniques in common between these two. And what you can see on the right is the histogram of differences is showing 2 millimag fluctuations, which means that at least one of these surveys is globally perfect, has global calibration variations below 1.4 millimags, which I think is amazing and is going to be worth a lot. Okay, so let me move on to astrometry. Here's a list of the different terms of physical models that go into the DES astrometric model. Again, I forgot to mention this, but the key to making a successful model that we can solve is dimensional reduction. We do not allow a free parameter for every pixel on the array, right? We don't even have a fine-grained two-dimensional solution. Things like the tree rings, we reduce to a radial function, for instance, right? So that we cut the number of free parameters in the model down to a number that our sample of stars can constrain well. And those dimensional reductions are all physically motivated. Right? Okay, so there's just a list of terms and how big they typically get. Let me jump to the results. Here is, so we make astrometric maps and we have smooth polynomials plus tree rings, plus some edge things going on for each CCD. If I take all the CCDs, photometric residuals for the whole survey, and I average them by position on a CCD and stack up all the CCDs, this is what the map looks like, where the little arrows are astrometric displacements, and you'll notice the scale is quite fine here. We're looking at fractions of a milliarcsecond. So we didn't put in any parametric function that could follow a shape like this, right? Because it's some crazy shape. But if you take the divergence and the curl of those arrows, you get this, and you see that it's a curl-free pattern, and it does have a divergence, which looks exactly like the connector that's on the back of the CCD. And if I remember my E&M, this is suggesting that there's a potential that's induced by that connector within the CCD. that's sourced by charge that looks like the middle diagram, right? That is causing these deflections in the CCD. So that is another pretty cool thing. Okay, other things to worry about that Rubin will want in their algorithms as well, and I think they already have, is that the CCDs move over time, especially when the camera is warmed up or cooled down. This is just an exaggerated diagram of how the CCDs and DCAM shifted during one warm-up cycle, which happened to be the worst one. Okay. Now, another thing that I want to point out, a wrinkle that we don't have that LSST-CAM will have for both astrometry and photometry is that they have field rotation. DCAM is an equatorial mounted telescope. And so unless it works out very nicely that there's a, an additive separation between things that rotate with the telescope and things that don't, then solving the LSST system for different rotation angles is going to be a big mess. Okay, so we should hope that there's a simple, rotating component associated with the camera. Okay, so another thing that's different from astrometry from photometry is that the stochastic signals from the atmosphere are much larger than the shot noise or residual errors in the fixed solutions for a single exposure of a bright star. Okay. And let me show you, here's a map of the residuals on a single exposure to our so-called fixed astrometric model. And if you're sharp-eyed and you can do vector calculus in your head, you may have noticed that this is a curl-free pattern. So this is the div and curl of that. And this is actually precisely what we expect from the atmosphere, because the atmosphere has index of refraction fluctuations. And the deflections should be the gradients of those. And you can see from the divergence that this is a streaky pattern, which is what we expect if the turbulence is being blown by the wind across the focal plane. And that also makes the astrometric errors asymmetric. So in a single 90-second DCAM exposure, these are the histograms of the distributions of major and minor axes of these astrometric errors, which you can see are typically about 5 and 8 milliarc seconds RMS, major and minor, or minor and major. Okay. On LSST, these histograms will look a little better because it's a bigger telescope. It averages over a larger patch of turbulence, but they'll also be worse because they're shorter exposures and they don't average over as much turbulence. So probably this will look similar in LSST. The sight may be a little better, which might help. Okay. So what can we do about this atmospheric thing? Well, the nice part of it is that if you look at the right here, this is the correlation function of astrometric residuals, like the map you saw before. And you can see that it has a coherence length out here around 10 arc minutes. And that means that we have many Gaia stars or high signal to noise LSST-CAM stars in each exposure, and we can use them to measure this turbulence and interpolate it, right? So because this turbulence field is almost a Gaussian random field, a Gaussian process interpolator should be optimal for this job. And I made a real quick run at doing a GP interpolation from a selected subset of stars, and I found that I could quickly reduce this residual variance by a factor of 8. So I think these 5 or 8 milli-arc second RMSs that we're seeing with an interpolation, GP interpolation exposure by exposure, we can reduce the atmospheric signal down to maybe a couple of milli-arc seconds per exposure, which is comparable now to the level at which we've solved all the fixed maps. And I have a undergraduate senior thesis student, Willow Fortino, and she is working on refining this. In particular, I won't go into details here, but we have devised a variant of the Gaussian process, which takes advantage of the fact that the 2D field has to be curl-free. Okay. So we end up with several correlation functions, unlike the correlation matrices, unlike just the one correlation matrix that a normal GP has. Or another way of saying it is that we correlate the X and Y deviations. We solve for those simultaneously in one GP. So this is a post-processing step that I suspect we'll end up wanting to do for every exposure. So that was what I was going to say about the photometry and astrometry solution algorithms. As I said, the algorithm itself is not that complicated. It's just a matter of being thorough with this additional wrinkle that there are these stochastic atmospheric effects in both that I think we can reduce substantially by using our own data. Okay. So I just want to say a couple other things, and whenever I hear Leanne's phone ding, I'll stop because these are not as essential. But we've worked on DES a couple of other things. One that is critical to photometry is sky subtraction. So we did come up with a new-ish algorithm for subtracting sky, and here we are distinguishing two kinds of sky. There's a sky background that you would get from a truly uniform sky. You know, the emission and scattering from the atmosphere is pretty uniform. Zodiacal light is pretty uniform. This includes things like fringing, okay? And this uniform pattern should repeat from exposure to exposure, but it might be driven by a small number of physical variables, like what's the moon phase, how far are you from the moon or from the horizon, how excited is the air glow at that moment, etc. So it's a perfect opportunity to do something like principal components, which we did. And then, so we have one step of sky subtraction that removes what we might call this repetitive sky. And then each exposure has its own, you know, zoo of other kinds of sky junk, which Robert referred to as, you know, the ghosts and the ghouls. And also you might think of, you know, the large halos around individual bright stars. In DES, we, you know, have a ray tracer that predicts for the brightest stars where the ghosts are going to be, and we pre-mask those regions. Steve Kent did that for us. But otherwise, we're relying on Sextractor sky subtraction algorithm to remove these and manual masking of the worst cases. So,
Gary, just to give you a 5-minute warning, my beeper doesn't seem to be very audible.
Okay, thank you. Feel free to tell me when it's done, because I don't have a clock here.
Okay, we've got 10 minutes left remaining, including discussion.
Okay. All right, so I'll just say that we find that images of diffuse objects are actually much better rendered with just the first part of the sky subtraction and leaving off the Sextractor local junk sky subtraction. And I'll show you that. Here is an image of a large diffuse object that showed up in our one of our images with the Sextractor sky subtraction run. And here it is with just the field-wide PCA subtraction done. And I went, you know, you can't do a PCA on 1,000 images of 2 billion pixels each, at least not that I know of. So we have some tricks to decimate the billion or so pixels into a much smaller number that you can do a PCA on, and then reconstruct these principal components at full resolution. And here's just large scale views of what the first 6 principal components of sky look like. And here's the first 4 principal components for G, R, I, Z, and Y. The first principal component is essentially some version of a sky flat and has the mean basically of the fringing and everything in it. The second and third principal components are clearly gradients across the field. And the fourth principal components have to do with a change in the amount of air glow relative to continuum, I think. And here you see the 0th principal component for G, R, I, Z, Y, where you can see the fringing appearing in Z and Y. Here's another close-up view of the 4 principal components in Z band, and again, mean, gradient. And then this one you can see has fringes in it. And I think what we're seeing in the fourth component is whether it's, say, moonlight or air glow that's dominating the sky. Anyway, this has worked really well. And I don't know what the status of this is in Rubin, but we'll hear about that later. Okay. The last thing that I'll just mention and not explain is a paper that we'll have coming out soon, which is that we used Balrog, which is the trademarked name of the DES source injection software, to compare the measured to truth for the flux and some low order moments of galaxies that are injected and then run through the whole pipeline, including sextractor sky subtraction. And what we can see, we make a pull diagram of the residuals of measurement to truth. And we can see that for the flux moment, there is a negative bias in the flux at about 1/10 of a sigma or so. And we believe that is due to a systematic over-subtraction of the sky in the sextractor algorithm. And in fact, if we do a local sky annulus around each object, that goes away. We also see that the sigma is 10% larger than the shot noise estimate of what this flux measurement should have for noise. And that we are fairly confident is due to the influence of undetected sources sitting beneath the shot noise in the images, which we can recover through some old tricks that have been around for a while, which is basically cross-correlating different images of the same part of sky so that shot noise cancel out. And I won't go through these slides, I'm running out of time, but I can talk to anybody later. And this should show up on archive. But essentially you can measure your undetected sources in a statistical sense. And that ends up being a 10 or so % change to the noise level that we expect for fluxes in G-band, actually in all the bands. So it's a non-trivial thing if you're trying to really be careful about what your measurement noise is. And in this plot, we just show that the measured sigma compared to the expected drops from the blue down to the red line dots here when we include this empirically measured undetected source noise contribution to our error matrix. And so now we're within a few % of getting exactly the right noise. Okay, so that was what I just wanted to say. It wasn't a lot about algorithms, but nothing we're doing is too sophisticated. It's just a matter of working through things that people had felt free to ignore in the past and that you can do when you have 100,000 exposures with the same camera and are willing to take some time. The main things, for this audience, I think, is that sky subtraction and noise, once you want to get them, understand them at better than 10% level, you have to start thinking about those. Everything we did should be readily applicable. In fact, a lot of it has already been, is already part of the software stack. So I'm preaching to the choir here. But in most cases, the scaling from DES to LSST will just be linear in the number of sources, with the main complication, I think, being that field rotation. So that's it. Thanks.
Thank you, Gary, for that excellent set of lessons learned from DES. Round of applause for Gary on Slack, everyone. I don't see any hands up yet, but we do have one question from Robert Lupton on Slack. Robert, do you want to ask your question? I'll have to unmute you first, just a second. Hey, Robert.
Okay, hi, Gary. Very nice stuff. One of the things that's always worried me about scaling from things like DECAM is whether you really scale to an 8 meter or a 6 meter, 6.5 meter, as the effective number of R0. And whether as R0 gets really large, the fact we have an annular mirror makes a difference. It's relatively narrow relative to high atmosphere, really good R0. I'm not sure we ever see those at Pachan, but theoretically that can change all the statistics. You get a non-redundant non-redundant sampling of our node.
Yeah.
So do you think the astrometry scales to an 8 meter or a 6 meter?
Well, I don't think my prediction of anything is accurate to the difference between those, but to start with. In the case of astrometry, what we're measuring is the mean slope of the wavefront across the aperture, right? So we're essentially taking the Kolmogorov spectrum and we're going to convolve it with the aperture. So you could figure this out, right, by smoothing Kolmogorov with the Fourier transform, you know, the Airy function for the full versus the annulus. And I suspect it'll be closer to the 8 meter result than the 6.5 meter result, but it's a guess.
Okay.
Okay, we have a question now from Colin Slater.
Just going back a minute to the correction using the 6 arcsecond aperture. I didn't quite understand how this correction is working because it's, I mean, I guess the question is why doesn't the aperture correction itself pick up this issue, or are you adding additional amplitude to that signal?
That's right. So we use 6 arcsecond apertures, right? And then for stars that are clear enough of neighbors, we can measure this 6 to 8 arcsecond increment. And we multiply that by 1.5 or 2 or some number that we determine empirically and find that it yields the most stable correction, the correction that has the lowest deviation between different measurements of the same star. So yes, we're using that annulus to essentially leverage a guess of the variance to infinity.
So that's kind of assuming that it's not really a scattering thing that you're correcting for, but some sort of overall transmission difference.
I think it's more of a, if it was an overall transmission difference, then we would be able, well, let me put it this way. The fact that this additional fraction of light at 6 to 8 arcseconds correlates with the error tells me that it's the shape of the outer part of the PSF where the light is going, that it's not just light disappearing in the atmosphere.
Oh, shape makes sense. Okay.
Yeah.
Interesting.
Right. We're basically asking how high are the wings of the PSF? And if they're sort of doing this, I don't know if you can see that, but that's what I think is happening. And Eli may have more to say about that, but it turns out, I guess, I wouldn't have, that it may be easier to change the atmosphere's, that the atmosphere's scattering properties may be more variable than its extinction properties.
Okay, that's helpful.
Okay, thank you. Conrad, you have a question?
Hey, Gary, amazing stuff. I have 2 quick questions. One is when you do this massive chi-squared minimization, I'm curious how many data points you have to reject in your rejection steps before you've converged. And the second quick question is, if you had one more parameter to add, which one would it be? What is the next thing you would want to add into the mix, or are you done?
Well, let's see. I don't know if this was particularly directed at astrometry or photometry, but let's see. Sorry, I already forgot the first question.
Rejection rate.
Oh yeah, the rejection rate. It's a few percent that end up thrown away, as long as we're careful not to, go into a globular cluster or something where the data is bad. Then as far as what else is important, I have to say I'm not really sure. I guess the one thing that I was pondering for photometry was, and actually, Eli and company have sort of done this, is to let the atmospheric properties, the gray terms or whatever, be some kind of Gaussian process through the night. so that we didn't have to treat each exposure as independent, but we were fairly flexible about what time scale the atmospheric transmission or might have. And we could do that at the level of, you know, an actual physical atmospheric model. How does the water vapor content, et cetera. I think last I heard, the FGCM, which is the global thing, let those things change maybe linearly during a night, the atmospheric parameters, but maybe we could try to be more flexible with that.
Okay, thanks.
Okay, we'll take one last question now from Eli and then move on. Hang on.
Oh. Hello. Okay, I just wanted to follow up on two things. So I'm going to be talking about different definitions of aperture correction because it's used by different people in different ways in my talk. And then, yeah, the Gaussian process thing would be interesting to put in for the especially for how the water vapor varies through the night, and that's something like that is been on my it would be nice to do, but there's been no particular need on the DES side, and I'll be talking a little bit about that as well in how that can be done on a just single exposures as the interpolant points.
Okay, thank you, Eli, and thank you again, Gary, for that very impressive presentation.